This is the first problem that I do for chapter 20, and it looks kind of finished. In fact, it is. I had recorded it, and then what happened, for some reason, it didn't want to save my recording, so I had to start over again, and I might as well leave what I had already written on there. Okay, so it says that a battery charger is connected to a dead battery and delivers a current of 6.0 amps for 5.0 hours, keeping the voltage across the battery terminals of at 12 volts in the process. How much energy is delivered to the battery? And so this is the information that is given in the problem. And in order to be in standard units, this one would have to be converted to seconds. Of course, 5 times 3,600 is those 18,000 seconds. Energy is what's asked for. What you find in the chapter is that power equals electric current times voltage, and then you have to go back to the energy chapter perhaps, where it says that energy is power times time, and that's pretty much it. Electric current times voltage times time, and then you get that in joules. And if you look at these three numbers here, 12 times 6 times 18,000 is probably going to be about a million joules. And when I had recorded it the first time, the one that I recorded that I lost, it really just took me also just 2 minutes for that. Down here, I introduced that you can do it a second way. From the previous chapter, you saw that either the previous chapter or the one before, it said that electric potential energy equals charge times potential, and so energy is equals charge times voltage. And then what happens is, because they don't give us the charge, but we know that electric current, this part here, and I can use a different color as well, this part here, electric current is charge per time, and then I just multiply that by time on both sides, so that time divides out and I can substitute the charge, and I come up with the same thing. I substitute electric current times time and come up with electric current times voltage times time. So the equation that is needed can be arrived at in two different ways. Alright, next problem. I had also already started it. This one is really straightforward. It says high voltage power lines are familiar sight throughout the country. The aluminum wire used for some of these lines has a cross-sectional area of 4.9 times 10 to the negative 4 square meters. What is the resistance of 10 kilometers of this wire? So that's just a matter of plugging in numbers. Use the equation that connects resistance with resistivity. Plug in the numbers. The area is given in square meters in the problem. The length is 10 kilometers, respectively 10,000 meters. And the resistivity, you look up in the chapter, it lists it for aluminum as 2.82 times 10 to the negative 8 ohm meters. Units, the meters or meter squared will divide out, and you're just going to be left with ohms. I want to show that FET actually lists this kind of problem, or I'm not sorry, not this kind of problem, but has an applet that this problem can be done with. So here it is. Physics Educational Technology from Colorado. It's easy to Google. And the one I'm looking for, and here I already went into physics, electricity, magnets, and circuits. And the one that I want to look at is resistance in a wire. Click on Run Now. There it is. And now I'm going to look at what I get from the book. The resistivity is 2.82 ohm meters, but I don't have that available. Notice that it gives me ohm centimeters, so I'm just going to do 0.82. There we go, which means I have to have a conversion from that to ohm meters. And then the length here, yeah, I don't have kilometers, I only have centimeters, so this one here is actually centimeters. And then it lists in the problem 4.9 square centimeters. But as much as I try to shift, the closest I can get is the 4.85, and then it course, here the wire change, you know, you increase the length, that's kind of obvious, and the resistance increases, and the resistivity increases, so there are more atoms in here, and so the resistance increases back to the point to 828, and then the square area increases, and you can see it's easier for the electrons to flow through there, so the resistance goes down. But I put it back to, what was it again, 4.85, and again, this one is in centimeters, and you would have to multiply so and so much in order to get it to 10,000 meters. But overall, actually, these two, 5.8, because my numbers are so close here as far as the digits are concerned, it should contain a 5.8 in for the result, and then the decimal point might be a little bit off, or it might be actually the same if you convert all these centimeters to meters. In any case, just wanted to show that that one is available on FET. For this one here, the resistance is relatively small, but we have to look at that in power lines. And by the way, this is on top of the problem. This is doing something on top of it. We have to look at that, well, there is some kind of energy loss in there, or power loss, which of course is times time. So the power lines take up some energy. And in the previous problem, I wrote this as electric current times voltage times time. And now they give us the resistance in the wire, so I'm going to use the Ohm's law and plug it in as that voltage equals current times resistance. So another I times R, which makes this one here an I squared, and R times time. And since in the power lines we like to use up as little power or energy as possible, of course the resistance should be small. One way of achieving that is make pretty thick power lines. And the other one is that the current should be pretty small, and that's why you see such high voltages on the power lines, because that high voltage, after it goes through a transformer from the power plant, the voltage is being stepped up, but the electric current is being stepped down in order to get as little of a electric current running through the wire as possible with, well, a very high voltage at the same time, so that the power loss within the power lines is relatively small. That's just on top of what the problem asked about, but I figured, hey, this is a problem on power lines, so I might as well mention that. The next problem says a blow dryer and a vacuum cleaner each operate with voltage of 120 volts. The current rating of the blow dryer is 11 amps and that of the vacuum cleaner is 4.0 amps. Determine the power consumed A by the blow dryer and B the vacuum cleaner. C, determine the ratio of the energy used by the blow dryer in 50 minutes to the energy used by a vacuum cleaner in 1/2 hour. All of this is really straightforward. So the power for the, let's see, which one was the first one here, blow dryer. Yes, so for the blow dryer, BD, I guess. Whoops. BD equals electric current times voltage. Both numbers are given in the problem, so just plug them in. Once again, 120 volts times 11 amps, so you should come up with 1300 watts. For the vacuum cleaner, VC, same thing. Electric current is given as 4.0 amps. Voltage is the same as the blow dryer, 120 volts. So that should come out to 480 watts. Those were parts A and B. That was supposed to be an A, and that's B. And part C is determine the ratio of how much one uses over the other, but they're run at different times. So that would mean the power of the blow dryer times the time that it's being used, and it was the 15 minutes respectively. Yeah, so for 15 minutes respectively 900 seconds, divide by the power for the vacuum cleaner. That was just calculated times the time for 30 minutes. That was supposed to be a 3 a moment ago, which is 1,800 seconds, and then equals, and then you're going to come up with so and so much more by the blow dry compared to vacuum cleaner with no units because a ratio doesn't have units. The next problem says an electric furnace runs 9 hours a day to heat a house during January 31 days. The heating element has a resistance of 5.3 ohms and carries a current of 25 amps. The cost of electricity is 10 cents or $0.10 per kilowatt hour. Find the cost of running the furnace for the month of January. Alright, notice that time is given, 9 hours times 31 days, and then we could argue if we're going to get the hours into seconds. I'll show that we don't have to in a moment. And the resistance is given and the current is given. That sounds like we have to use the power equation. So electric power equals electric current squared times resistance. Notice that the voltage isn't given. And then at some point we're going to have to come up with how much energy is being used. Well, that's where the time comes in. So of course E equals power times time, which means we have to use this kind of equation here, I squared times R times T. And of course what they're asking about is the total cost. Let's see, I'm going to start over. I wanted to write total cost. So the total cost there we go. Equals the rating they give us here, the 10 cents per kilowatt hour. Well, the kilowatt hour is a unit for energy. You know, the watt is in here times time. That comes out to energy. It's not the standard scientific unit, but it can be easily related to the joules with a certain conversion factor. In fact, the conversion factor would be 3.6 million. And so I would have to multiply this here by the energy that we would be calculating in order to get rid of this unit here. My energy up here will be perhaps in joules or kilowatt hours, and then the unit would divide out. So at this point here, it's a matter of plugging in numbers. The current is given as 25 amps. The resistance is given as 5.3 ohms, so 25 squared times 5.3. The time I mentioned a moment ago is given in hours times days, so 9 hours times 31 days would be 279 hours. I would keep this one here in hours because when it comes to converting, you really don't need to because it already says watt hours. So when you keep it in hours, actually what you're going to come up with here is not joules but watt hours. Only if I converted that hour here to seconds, then I would get joules, but I might as well leave it like this. So I come up here with watt hours, and then I shift the decimal point 3 times, and I come up with kilowatt hours, which then divides this unit here. And so I plug that in. Basically, you come up here at watt hours converted, shift the decimal point 3 times because of the kilo, multiply by $0.1, and you're going to come up with the total cost. And that would be in dollars. And on your energy bill, that's actually what you see is how many kilowatt hours you have been using. this one here, the result should be in the neighborhood of about $100 when you're done with it.